Hi everyone. So today I would like to discuss some properties of the estimate for also some testing on the linear regression coefficients. So last time we studied that the beta hat is equal to X transpose X inverse times X transpose Y. So here the beta hat is the estimate intercept and slope. So beta hat is equal to this vector of beta naught hat and beta 1 hat. And this quantity is just estimated. So it's not really a constant, but it's random. So it really depends on the data. So think about the situation. So we have the true trend line. So that is the assumption of the linear model. So the true trend line is y is equal to beta naught plus beta 1x, but this is not observable. Then we observe several data points like this, and we estimate line from these points. So probably the line is around here. So it's not exactly the same as y is equal to beta naught plus beta 1x, but this is y is equal to beta naught hat plus beta 1 hat x. So each time you observe data, that you have the different line. For example, another data set maybe like this, and maybe estimate maybe this line. So it's slightly different each time. So it has some variability. So how much variability it has? So we discuss that in this video. So variability of beta hat is estimated by, expressed by just this formula. So basically variability comes from this y. So x is assumed constant and y is random because y is equal to x beta plus epsilon and epsilon is random. So the random quantity is here. And actually, except for this part, the remaining part, X transpose X inverse X transpose X beta. So this is just beta, right? So just X transpose X cancel. So the remaining term is here. So this basically brings in some variability. So X transpose X inverse X transpose epsilon. So this term causes the randomness of beta hat. And to be exact, what's the variance of beta hat? So this theorem gives the formula. Beta hat is actually the X transposed X inverse sigma square. So here sigma square is the variance of epsilon. So to be exact, the variance of the variance of beta hat means this matrix. So so-called variance covariance matrix. So diagonal terms are variance of beta naught and variance. So here the y is equal to a plus bx. So sometimes I say this as beta naught and this as beta 1. But anyway, so the variance is in a diagonal term, and off diagonal term we have covariance. So covariance, actually, this is equal to the standard deviation of A times standard deviation of B, that is square root of variance, times correlation coefficient. So rho is correlation coefficient. So correlation coefficient of A hat and B hat. So this matrix includes the three information. So three pieces of information. One is the variance of A, the other is variance of B, and another is variance of B, and the other is the covariance of A and B. And you can see that the y is equal to x beta plus epsilon, and x is n by p matrix. The p is the number of parameters. So actually x transposed x, that is the p by p. So this is p by n, n by p. So in total, this is p by p matrix. And sorry, to be exact, this is 2, sorry. So this is the n by 2 matrix because the first column is constant and the second column is the variable x. So this is n and n by 2. So totally the X transpose X is 2 by 2 matrix. Then inverse, then sigma square is just a scalar. So the variance of beta hat is 2 by 2 matrix. Yeah. And sigma square is not observed. So sigma square is the variance of error term, but even error is not observed. We have no way to exactly know sigma square. But the sigma square can be estimated by this, the mean squared error. So the 1 over n minus 2 of epsilon I hat square. So here we have n minus 2 because we have estimated 2 parameters. Usually we only have one estimate. So we have to estimate the population mean first, then the variance, we have 1 over n minus 1. But here we estimated 2 parameters to calculate epsilon hat square, so that we have n minus 2 in denominator. So we plug in these numbers to estimate the variance of beta hat. And how to prove the variance of beta hat formula? So this is somewhat straightforward, but some calculation we need. So at first, we want to mention that when expectation of some vector is 0, then variance of vector E is expectation of E transposed. So just to think about the case that E has 2 components, E1 and E2. Then what is variance of E? Variance of E is, okay, so off-diagonal term is covariance of E1 and E2. And the diagonal term is variance of E1 and the variance of E2. So the off-diagonal part is both covariance of E1 and E2. So this is actually just the expectation of, the vector E1, vector E1, E2 times vector E1, E2 transposed. So you can imagine that in general, if E is n-dimensional vector, still the variance of E is expectation of E transposed. So using this formula, we can prove that this variance of beta hat formula. So beta hat is at first, remember that the beta plus this term, we have already shown in the previous slide, but the variance, to calculate variance, the constant term doesn't matter. So variance of, in general, the variance of Z and the variance of Z plus C, where C is constant. So these are the same. So we can just ignore beta. Then what's the variance of this? So we use this property. The variance of E is expectation of EE transposed. So at first, this is just exactly the same as this term. Then we transpose. So transposed part is here. Then, okay, so we transposed one by one. So in general, if we have matrix AB, the transposed is the B, AB transposed is the B transposed, A transposed. So we at first, the transpose, that is epsilon, okay, so then we transposed X transposed. So E transpose, epsilon transposed and X, and actually you can show that the transposed matrix of this is again this matrix because X prime X, this is already the symmetric matrix, and inverse is also symmetric, so the transposed, that does not change anything. Yeah, so now we have, okay, so this term and this term, but these are constant. Remember that only epsilon that brings in the randomness, so the constant. So you can always put the constant out of expectation. So essentially this is expectation of epsilon, epsilon prime. But the expectation of epsilon, epsilon prime is equal to sigma square times identity matrix with the dimension n, because the epsilon is assumed to be independent. So expectation of epsilon I, epsilon j is equal to 0, because these are independent. So you can decompose expectation, and expectation of epsilon I and expectation of epsilon j are both 0. So this becomes 0. And if I is equal to j, diagonal term, this is sigma square. By definition, the variance of epsilon I is sigma. We can get this equation. So actually this disappears. We only have sigma square, but the identity matrix is the same as multiplying nothing. So just think about the green part. And the green part, there's still the x prime x inverse and the so only the last term remains. And then we get the sigma times x transpose x inverse. So now that we completed the proof for the variance of beta hat formula. And I would like to add the one explanation on how to interpret the off-diagonal term of variance of beta hat. So the variance of beta hat is, okay, so we proved that the sigma square times x transpose x inverse. And okay, so this is the variance of the A hat and the variance of B hat. And this is off-diagonal term, the correlation coefficient times the standard deviation of A and the standard deviation of B. So here we have the same thing. And what this correlation coefficient between A hat and B hat means. So A hat is the S and B hat is estimated slope. So if rho is equal to, okay, so rho is equal to 0, it's independent. But if rho is less than 0, then A hat and B hat negatively correlated. If rho is positive, A hat and B hat are positively correlated. And for example, what happens in this figure? For this kind of data, you can actually see that this estimated rho is probably negative because this red line, so red line and the black line are both estimated regression line, and red line, actually the smaller slope, smaller b hat, you can see compared to the black estimated line, the b hat for red line is small, so the slope is less steep. And how about intercept? Intercept, actually, you can see the larger intercept because data are mostly on the positive part. Actually, all points are for the positive x. So if slope is small, then intercept actually gets larger because if the straight line is steeper, then it goes down more when x is equal to 0. So the red line, we have larger A hat. So probably in this case, the rho hat is negative. If rho hat is positive, probably it's a different situation, such as all data points are on the left-hand side of y-axis, or maybe the slope is negative, or such a situation. So you can actually see the meaning of the estimated rho in this setting.